Good afternoon. This is Robert Brown at Iowa State University. I'm the director of the Bioeconomy Institute, and it's my pleasure to host today's conversation. I'm very pleased to be able to have Dr. Michael Wang join us. I think I've known Michael for 20 years. He's been at Argonne National Labs longer than that, and he probably doesn't know that I've known him that long. I've just been following his work. His work on GREET is nationally, internationally recognized and has been extremely important to work in biofuels over the last several years, and now is becoming increasingly important as we look at issues of carbon removal. I'd point out that Michael is an Argonne National Laboratory Distinguished Fellow. He's a senior scientist and the director of the Systems Assessment Center for the Energy Systems Division. He has been with Argonne since 1993, and his research interest includes several things. He works in evaluation of energy and environmental impacts of vehicle technologies, transportation fuels, and energy systems. He does assessment of market potential of new vehicle and fuel technologies, and he examines transportation development trends in emerging economies. And I'm just going to add again, he's at the center of work on carbon removal at this time. So we really are pleased to have him join us today. I'm going to start by asking Michael, if you would describe your role at the Argonne National Labs beyond this little statement I've made.
So, Robert, thank you very much for having me here for a lunchtime conversation. And I hope when we all go normal enough time, or we can sit together in a room to have lunch and casual conversation. But with that said, again, thanks for your intro. So I've been working in Argonne National Laboratory since 1993, so it's almost 30 years, and it's been a long time since I moved to Argonne from UC Davis. And so as you all can imagine, I came from Aggie school in California, and in fact, I went to an Aggie school back in China Agriculture University. So I have a long history associated with Aggie schools for a long time. So after I came to Argonne, I work in the energy field, especially the transportation energy field, to do assessment of environmental and energy sustainability of different technologies, including new fuels and advanced vehicle technologies such as electric vehicles, fuel cell vehicles, together with biofuels in internal combustion engine technologies. So we, Robert, as you introduced, we developed the GREET LCM model to help us quantify the environmental performance of different fuels and technologies. And our sponsors primarily DOE, but we do work for USDA and Department of Transportation, in fact, FAA, and several other offices in DOT. And we have had a working relationship with state agencies such as the state of Illinois, state of California. And we have had a long collaboration with universities, and we received graduate students coming to Argonne for internship, and we have had a few postdocs coming from our state. So we look forward to seeing more collaborations between the university and Argonne, and Robert keeps setting us the talented students, and we definitely need more new people in the field.
We'll see what we can do, Michael. I know they've all enjoyed their experience. Now, I mentioned in my introduction, you work with the GREET model at Argonne. Many in the audience are unlikely to be familiar with it. Could you provide us an overview of its function and why it was even developed?
Okay, yeah, sure. So GREAT is a life cycle analysis model. So your life cycle analysis in a different way, we can think about to do analysis on the supply chain of individual product. For example, if we use ethanol, we want to see, okay, how ethanol is produced and what feedstock, what input to produce the feedstock in the US situation. Corn is the major feedstock, so how corn is produced, what are the chemical inputs for corn farms. So take into account the critical input and of course emissions along the supply chain. So that's what life cycle analysis is all about for specific product or specific technologies along the supply chain. So why we develop the GREAT LCM model? So when I came to Argonne, actually before I came to Argonne, when I worked on research projects back in UC Davis in graduate school, we had some projects for the state of California to evaluate back there we call alternative fuels. So methanol, ethanol, compressed natural gas. Of course, my major professor was interested if we have a fuel switch. What does that mean besides combustion of the fuels? How the fuels are produced upstream? What are the environmental footprint of the upstream activities besides the vehicle operation implications? So, I studied LCA back in graduate school in UC Davis. When I came to Argonne, we had a multi-lab project for DOE. Back then, DOE started to evaluate electric vehicle, hybrid electric vehicles potential in the US. And the multi-lab team work on how electricity is produced and how electricity is used. So I was responsible to look at the environmental footprint of electric vehicles and hybrid electric vehicles in '93 when I came to Argonne. And use what I did in UC Davis and put things in spreadsheet along the supply chain of EVs, HEVs, and internal combustion vehicle technologies for that project. So that's kind of the beginning of the GREAT. So after the project is over, DOE asked me, so how about you wrap up what you did for the project and do some customization and share your spreadsheet with others so others would not go through the same process as you did. So that's what I did in '94 and released a very simple spreadsheet. So that's the beginning of the GREAT. So if some of you are interested in the first version of the GREAT release in 1995, you would laugh me up the doors. Gosh, it's this simple. It was very simple. But it's kind of basically put it in spreadsheets to help others not to repeat the same steps as I did. So.
Super. Now, I want to focus a little bit on carbon. When people say, well, what is this? What does it involve to manage carbon in the atmosphere? And I say, just think of it like a bank account. You make deposits, you make withdrawals, and the difference is how much you have in the atmosphere. Now, of course, it's a lot more complicated if you're not getting receipts for your transactions. When you use GREAT, how do you actually go about tracking carbon in this spreadsheet as you've described it? And how would you describe the uncertainties in tracking these flows of carbon?
Yeah, this is a good question. So for people working in the engineering field, this is somewhat a little bit difficult to comprehend, because for those of us with some scientific and engineering background, we want measured data to support our hypothesis. And let's say if we have a hypothesis, we go to the lab and generate data to see whether our experiment can support our hypothesis. Life cycle analysis is somewhat different. So Robert, as you put, it's accounting. The financial accounting, we all know how we do our financial accounting. And we track down our numbers in and numbers out. Carbon is similar thing. We account carbon in and carbon out. Now, the difficult part is we cannot ask people to do a measurement on the supply chain for a specific product. We have measurement for specific activities, but we can't just ask people, say, okay, now you need to do a measurement on the supply chain of our product or technology. We have to rely on measure the data in specific area and integrate it along the supply chain. So people often ask, okay, so for integration of the data from different fields, how do you verify? And my point is, you can't verify LC results on the supply chain. It's just that the system integration make verification difficult. What you can verify is the specific data for the specific activities on the supply chain. That's where experimental data become important, and the plant operation data becomes important. So we can control the data gets into LC and verify the data, but in the end, we can't verify LC result. So that's the reality.
So I can imagine if you're dealing with a fossil fuel, I've got this resource and I can measure the carbon in it and I can consider the transport, et cetera. Once you start talking about fuels produced from agriculture, like biodiesel or ethanol, it seems like it would be extremely difficult to provide the contribution that agriculture plays in either a positive or net contribution. Can you tell us how you handle that for those? Because I know you've done a lot of work with ethanol and biodiesel.
Yes, yeah, and it is more challenging for biofuels than for fossil fuels, because fossil fuels are well established. We have over 100 years of history for fossil fuels. For biofuels, even we push back to the beginning of the U.S. core ethanol program in 1980, we only have about 40 years of the history. And the supply chain of biofuels are more complicated than the fossil fuels. You alluded us to that. Let's say for core ethanol. The core ethanol plant, our one has many core ethanol plants spread all over the state. So for core ethanol plant, we can see, and the plant has data, so okay, how much core I get, how much natural gas I buy, how much electricity I use. Plant is somewhat easier. The core farms are somewhat difficult. So if we look at a core ethanol plant, we have so many farms to supply corn to this specific plant. Each farm is different. And we know farms use fertilizers, use diesel fuels, use electricity and propane. But farmers have hard time to track down how much I use. They have some bills, but the bills are more on the cost than also the amount of natural gas I use and the amount of fertilizer I use. I know how much I pay. So that's the tough part. And for certain input, it's going to be for a specific farm operation. It's not specifically for core farm, but it's for this farm operation. This farm may have soybean, may have corn, and some other activities. So how do you attribute some of the input to corn? That's a little bit challenging. Even more so, we heard the debate of land use change. So land use change is from our policy, from our national policy and international effect, so global effect. So that's where your individual plant cannot track down. The individual farms definitely cannot track down. And we only use economical models to simulate the so-called indirect effect, such as land use change from corn ethanol. So there are lots of complications involved in biofuels. And that make biofuel LCM more complicated than fossil fuels.
And certainly we still see a lot of, when I read the newspaper, still talk about, well, the impact of biofuels is worse than fossil fuels, reflecting some of the uncertainty that exists. But I'm just curious whether you have would make a blanket statement about are biofuels worse than petroleum fuels in terms of their net greenhouse gas emissions?
No, not from our research. So our biofuel LC studies in 1996, and we have the first publication in 1997 to document back there how the U.S. corn ethanol performed. Since then, we continue to monitor the progress of the agriculture sector, the biofuel sector. And we see, as we see for many other sectors, technology helps the biofuel sector to progress, and we see a continual improvement in energy efficiency, the yield in farms. All those improvements helped the carbon footprint for biofuels. So based on our most recent evaluation of the U.S. core ethanol industry, even including the indirect land use change, and we see the U.S. core ethanol reduce greenhouse gas emissions by 45%. And some studies 45%. 45%. Some studies conclude about 50%. And EPA, as the EPA 2010 evaluation shows 21%, but that was 2010. And California Air Resources Board shows about 20% reduction. And I can go to the nitty-gritty details of why your different agencies has different
I'm sure
studies.
There's many reasons, yeah.
Yeah.
Okay.
And on the other hand, the biodiesel and renewable diesel give us larger reductions, above 60% reduction in greenhouse gas emissions.
Well, I want to ask you one more question, but I want to make sure, before I open it up to the audience, I'm going to encourage the audience to start posting their questions. I think there's both a chat function and a Q&A function. I think we want you to put them in the Q&A section, and I'll read those. And if I can't see them, maybe Dana, who's on as well, will help with that. So here's my final question. So many of us are very familiar that there are targets in terms of how much we want to limit CO2 increase in the atmosphere over the next several years. But I think many of us don't really have a good sense of how difficult that will be for us to do. I mean, particularly how it impacts our daily lives. And as an example, several years ago, there was an international effort to reduce chlorofluorocarbons as refrigerants. In my view, that was going to be really impactful, but in many respects, it was transparent to most of it. It happened, they were successful in doing it, and we're moving on. Do you think the same will be true for reducing the rate that CO2 is going in the atmosphere, or removing that in the same fashion chlorofluorocarbons, or do you think this is going to be much more impactful on our daily lives?
Well, it should. to reduce greenhouse gas emissions is a major challenge. And we all know now globally we are facing this major challenge. And if we're going to control the temperature increase below 1.5 degrees C, we know we need deep decarbonization globally. And the US, of course, now is #2 greenhouse gas emission country who have major responsibility to reduce our greenhouse gas emissions. And by the way, as we all know, China is #1 and the US #2 in terms of emissions. So right now in the international arena, we talk about international policies to push new technologies into a marketplace. The International Civil Aviation Organization has a program to reduce the aviation fuel carbon footprint. The International Marine Organization now is contemplate a program to reduce marine fuel carbon intensity. US has, California has LCFS, and US EPA has RFS, and the Canada now is in the final stage to put its own clean fuel standard up. So policies are going to be key to push technologies into the marketplace. But from bottom up, each of us as individuals, we can make certain choices to help to use the technologies with less carbon footprint. For example, we all drive to shopping, to work. We could pick different cars with better fuel economy, or better or biofuels, battery, EVs, hybrid electric vehicles to reduce our transportation carbon footprint. Midwest in January, heating is a major issue for our homes. If we can turn our room temperature by 102 degree low, we know we'll save some energy, we'll save some money, and we'll reduce greenhouse gas emissions. So these are the bottom-up activities we as individuals can do. So we need top-down policies, and we need bottom-up actions from each of us.
Thank you, Michael. The questions are starting to come in, so I'm going to ask them in the order that I'm receiving them. And so we'll see how far we can get through them. Okay, so Emily Heaton is asking if, for your comments on models the USDA is considering for farmers to do their own LCA on farm. And examples were Comet Farm, nutrient tracking tool, etc. Curious if we are on the right track in doing this kind of on-farm analysis.
Yeah, this is a good question from Emily. So yes, USDA so far has some voluntary programs to incentivize individual farmers to reduce their greenhouse gas emissions. And Comet definitely is used to assess the soil organic carbon changes for certain farming practices. There are some other tools to track down the N2O emissions from reduced nitrogen fertilizers use. So those activities have some impact, but the impact has not been as significant as some of us hope, because the voluntary program's carbon price was somewhat lower. And I remember the carbon price was probably in the $10 to $15 per ton for CO2. So it helps, but the incentive is not large enough to make farmers have significant change in their practice. Look forward now with what's being discussed in Washington, D.C. There will be some significant programs to be in place in the next several years in the USDA. And I hope those programs will have the carbon price to higher level. For example, LCFS is carbon price around $200 per ton of CO2 versus up to $15 for those programs.
Very good. Here's another question. This comes from Maria Wellish. It has to do with harvesting corn stalks for use for various uses. Are there any greenhouse gas emissions associated with removing that stover and utilizing it? Where do they come from? She's asking if you have a good literature source to access on that topic.
Yes, yeah, we do. I know our one state university has done extensive research for to use corn stove for biofuel and bioenergy in general. So corn stove now left in the field has some functions for soil health, and we all know the stovers has some functions. And we also know in the last 20, 30 years, the corn yield has increased significantly. Together with that, corn stover yield has increased significantly. So with the increased amount of stover left in the field, there are some general consensus that if we remove some amount, roughly a rule of thumb, maybe up to 1/3 of the stover removed from a field for bioenergy and biofuel productions, that will not have significant detrimental effect on soil health. And yet we can use to produce biofuels and bioenergies to replace fossil fuels. And we've done some simulations on the soil organic change when we remove the sustainable amount of stover. There are many other organizations and publications in this area.
Very good. Now here's somewhat related, it's certainly an indirect land use question. If the GREET model is used in the US, but not by other countries, does that create an incentive for crop production to go elsewhere outside of the US?
Well, actually, GREET, GREET is primarily used in the US, but we do have a large international user base. But admittedly, GREET is not used in Europe. Europe used some other calculators to evaluate carbon footprint of different biofuels, including the US corn ethanol and biodiesel from US soybean. Unfortunately, those models generate somewhat higher carbon footprint values for the US biofuels. So that has created some trade barriers for US biofuels in Europe. And I know USDA has been working on this for over 10 years with EU, but so far EU still use their estimated carbon footprint of US biofuels. And in that regard, the EU used the EPA value 21% reduction for corn ethanol versus the new studies, including ourselves. So there are some talk with EPA and to convince EPA to update EPA's value. That will help us for the US biofuels in other countries. So I can say GREET has not been a barrier, but we do have some other barriers for US biofuels in other countries.
Thank you. Brian Sievers, who's a pioneer on on-farm anaerobic digestion here in Iowa, raises the question that they're looking for new pathways to produce renewable natural gas from sources such as biomass, beef cattle manure, and poultry manure, but are experiencing restrictions to the development of these new pathways, whether it's CARB or LCFS programs. What advice or suggestions do you have that might allow us to enhance our efforts to create new beneficial pathways for these on-farm digester facilities that go beyond the traditional Tier 1 pathways associated with dairy and swine manure from open lagoons?
Yeah, California already have tier 1 CIs for RNG from different feedstock animal waste, and I do not know if they have crop residue-based RNG, but animal waste is well established in LCFS. So for tier 2, definitely it takes longer time because there is a long waiting list in California Air Resources Board. But tier 2 mechanically it's open for petition in front of CARB. But I've seen some debate in the last 1 to 2 years on RNG. RNG has significant carbon benefit. Some of the pathways based on animal manure, the CI can be as low as a negative 300 grams per megajoule versus core ethanol's carbon intensity, depending on the facility is 30 to 60 grams. Negative 300 versus that. So the negative 300 grams generates significant monetary value with $200 per ton of CO2 there. But now, there is some pushback on RNG. So, I hope people working in the RNG space keep eyes on this pushback. The negative 300 grams significant amount is from the so-called counterfactual scenario methane emissions. That is methane emissions from conventional manure management. So some NGOs now want to give a cap to how much credit you can take from conventional manure management, CO2, methane mitigation. That can have a significant impact on RNG carbon intensity values.
Very good. Here's a question from Mike Castellano related to corn stover removal as well. He notes that in continuous corn systems, there is strong evidence that stover removal reduces nitrogen fertilizer requirement, and some evidence that it may increase yield. And his question is this idea credited in the GREET model, to your knowledge?
Well, yeah, we're aware some research result as this comment indicated. On the other hand, there are large uncertainties. In some cases, remove in northern Iowa and southern South Dakota could help increase yield, but in many areas, remove of stovers could have some incremental effect. For example, in some areas, when you remove stovers, you remove nitrogen in stovers, which would be available for next season's crop growth. So in that case, you need some supplement nitrogen fertilizer for the amount of nitrogen you removed. So WCAP took a conservative approach in GREET default configuration. That is, we say, okay, if you remove a ton of stover, we can estimate how much nitrogen you removed. Then we say we're going to next season to supplement that amount of nitrogen into the soil to make nitrogen balanced before and after stover removal. So it is a somewhat conservative approach to address this specific issue.
Sure. The audience recognizes we have a real expert on the line, so you're getting some really expert, detailed questions that require your expert knowledge on it. So here's one from Shannon Baucom. When measuring the carbon intensity of swine farms with pit lagoons in closed vessel, why is it assumed the temperature of the deep pit changes with the ambient temperature?
Yeah, that's a good question. And I imagine she's very deep into EPA's warm mountain. So
We've
EPA's
got a lot of
warm.
experts on the line
Yeah,
too.
yeah,
So,
right.
okay.
Yeah. I'm glad we have so many people deep into a specific area. So the warm model, can generate emissions based on the temperature, based on the aerobic digestion process. Many other models and IPCC is that one. So many models generate methane emissions based on the ambient environmental conditions. Temperature is a key variable for your methane generation. So a good question. So for the closed system, let's cover the system to manage the methane emissions. So I have not get into the details of the closed system methane generation. I imagine first you need to have methane generation, which is somewhat temperature dependent, and you need ambient temperature. And then you add the control. Since now you have the closed system, so methane is not just simply getting into the air, you capture that, you seal the system. So the control would be on the top of the generated methane emissions. But what we found out, the data is very spare for your methane emissions of animal waste, landfill. Landfill generates a large amount of methane emissions. As we rely on the available models, and we see data is somewhat old. Models based on very sparse data, and there's definitely more room to improve those simulations, which we base on.
Leanne Wilson has a question that's getting a lot of press in Iowa because there's 3 pipeline proposals, carbon dioxide pipeline proposals. So she points out that one of the objections to such pipelines is that this is a temporary need, potentially, that ethanol may be phased out relatively soon. Do you agree with that assumption or hypothesis?
Well, maybe Leah is more pessimistic than me. I think core ethanol plant will stay. I mean, we know gasoline market is going down because of electrification of passenger cars. But we also know we already have more than 200 million vehicles, cars, not duty trucks, SUVs on road. And we know each car lasts average 15 years. Mm-hmm. So it's going to take a long time to gradually phase up the internal combustion engine vehicles to use liquid fuels. So the gasoline market will be down, but it's going to be a slow process. So with gasoline market there, ethanol will have some demand. But on the other hand, there are some new effort to convert ethanol to jet, because aviation is one of the so-called hard to electrify transportation subsectors. So there are new efforts. Some ethanol plants now contemplate to convert ethanol to jet to serve aviation fuels. But with that said, we know a large amount of CO2, biogenic CO2 from the fermentation process. That's very high purity CO2, over 95% CO2 purity. Some of the plants now sell the CO2 to beverage industry, but still a large amount can be shipped to some geologic formations for sequestration. So I've been kept you're reading articles about the debate in Iowa, the CO2 pipeline. So a full series about deep decarbonization, we have to take into account CCS, that's carbon capture and sequestration. And ethanol plant is your low-hanging fruit for CCS because the CO2 purity is so high, you do not need clean up before you set to power plant.
Okay, good. Here's another real technical question. I'm going to paraphrase a little bit. It's from Eric Banks, and it has to do with challenging the default baseline assumptions of the California Air Resource Board CARB, LCFS, low carbon fuel standard. So how do you go about challenging default baseline assumptions? And his example is the assumption of 30% of volatile solids in effluent for existing digesters.
Yeah, so yeah, you can. So yeah, this gets to the tier 2 petition. So yeah, the process is open, and but you're forced. You're waiting in the line. So now there is a long backlog. So when your petition is going to get to their desk. Many people are frustrated because many people submit a petition as they're waiting. Of course, CARB has major challenges. They're short of people. If you look at their website, they'll look for people. They'll look for capable people to join the LCFS team to help. And COVID does not help. So they'll work from home. And for certification approved for work from home, it's hard because sometimes they need to have group discussion. So we have a lot of interactions with the LCFS team. Their leadership is as frustrated as the people petitioned to them. So yeah, it is a long process. And let's say now it is your turn. Now you get your case in front of the team. They still have technical questions to ask you as they want credible data to back your assumption to challenge their assumption.
Sounds intimidating.
It is.
Well, let's move on. We'll go back to the LCAs. This question comes from Lisa Schulte Moore. What are some of the key research needs or data gaps that need to be filled in terms of improving biofuels LCAs? In other words, how do you reduce the uncertainties that currently exist in some of this modeling?
More data will always help, and the facilities are my less concern, and the farms are my major concern. Especially now, some of us has been pushed the regulatory agencies to open feedstock certifications. As we all know, LCFS, RFS do not open feedstock certifications. So in those programs, feedstocks are used as national average. So if you do better than national average, does not help you because the programs do not open to certify your lower carbon feedstock. We've been talking with CARB, we talked to EPA about open feedstock for certification, as well as facilities for certification. This is tier 2 certification. But they always ask us hard questions. How am I going to make sure I have credible data to show me the individual farm CRs? Because individual farm CR is hard to certify the individual biofuel plant. Furthermore, we also open the SOC certification. If we're going to ask them to open feedstock, we might ask them to open SOC together with farm input, energy input, and chemicals input. SOC certification is even more hard. Let's say the so-called permanency issue is real. If I stop certain practice, do I still anticipate the carbon sequestered in the soil stay in the soil or add up in the air? So yeah, these are real issues.
And it looks like we have reached the end of our program. So I want to again thank you, Michael, for joining us. You had some very insightful answers. And you handled some very technical questions.
But we have
insightful got all that information
too.
up here. So
yeah.
this was wonderful. So I want to invite everyone to our next one as we end. That's going to be Dr. Kelly Bergman, and that's going to be on February 16th at this same time. I hope you can join us then. And again, thanks very much, Michael. It was a pleasure talking to you today.
Okay, thank you. It's good to see you again. Okay, bye.